Hello everyone, I'm Ramna from BSc Chemistry Honors final year, and today I'm going to read a chapter Electronic Spectra. So, introduction of electronic spectra. It has been discussed in the last chapter that when molecules absorb energy in the microwave region, it transitions between the rotational levels take place, giving rotational spectra. Similarly, if the energy is absorbed in the near infrared region, transitions take place between the vibrational levels accompanied by those in the rotational levels, giving vibrational rotational spectrum. However, if the light is absorbed in the visible region or ultraviolet region, electronic transitions take place, giving electronic spectra. A number of other processes also take place on absorption of light called photoprocesses. These may be photophysical processes such as fluorescence and phosphorescence or photochemical reactions. The branch of science dealing with such processes is known as photochemistry. In the present chapter, we shall take up a brief study of electronic spectra, whereas photochemistry will be discussed in the next chapter. Now, electronic transitions and band spectra. So, theory of electronic band spectra. Just as there are electronic energy levels in an atom, there are electronic energy levels in a molecule. Also, however, there are no simple formula available for the energies of these electronic levels except for the hydrogen-like atoms. Electronic spectra are obtained when the electrons in a molecule are excited from a lower electronic energy level to a higher energy level. However, if the electronic transition is accompanied by vibrational and rotational transitions, the total energy of the molecule in any state is the sum of the electronic energy, vibrational energy, and rotational energy. If and E nu and Er represent the electronic energy, vibrational energy, and rotational energy respectively of the molecule in the initial state before transition, and E dash, EV dash, and Er dash the corresponding values in the final state after transition, then we have energy of the molecule in the initial state. E is equal to E plus EV plus Er. Energy of the molecule in final state, E is equal to E dash plus EV dash plus Er dash. So energy change involved in the electronic transition will be given by del E is equal to E dash minus E dash E plus EV dash plus Er dash minus EE plus EV plus Er. E E dash minus EE is minus EV dash minus EV plus ER dash minus ER is equal to del EE plus del EV plus del ER. But according to Planck's quantum theory, del E is equal to h nu, which is equal to hc nu bar. Hc nu bar is equal to del EE plus del EV plus del ER. Nu bar is equal to del EE plus del EV plus del ER upon hc. As for a particular electronic transition and for a particular vibrational transition, del ER can have different values within the same vibrational energy change of the same electronic energy level. A number of closely spaced lines are obtained. This constitutes a band. For each vibrational transition, separate band will be obtained. Thus, due to different vibrational transitions for a particular electronic transition, a set of bands is obtained called the band group or band system. Each electronic transition will give a band system, and hence the complete electronic spectra involving different electronic transitions give rise to a series of band groups. Thus, the electronic band spectrum obtained for a gaseous molecule is quite complex. In spite of the complex nature of the electronic band spectra, these are preferred over the other types because these are obtained in the visible and ultraviolet regions, so that these can be easily photographed and studied. Calculation of dissociation energy of molecules. A study of the electronic band spectrum reveals that at one end of the spectrum, the distance of separation between the lines becomes smaller and smaller till ultimately the line spectrum vanishes and space of continuous emission starts. The frequency corresponding to the point where the line spectrum vanishes is the frequency necessary for dissociation of the molecule into atoms. Thus, electronic band spectrum can be used not only for getting the information as given by the vibrational rotational spectra, but it can also be used in evaluating the dissociation energies of the molecule. Potential energy curves and Frank Condon principle. The explanation of electronic band spectra and dissociation energy can be early understood in terms of potential energy curves and Frank Condon principle as follows. The potential energy curve of a diatomic molecule is obtained by plotting the potential energy of the system versus internuclear distance between the two approaching atoms. The curve obtained is of the shape shown in figure. However, even at the minimum energy position represented by point x, the atoms are vibrating. Therefore, the potential energy keeps on oscillating about the minimum position. The vibrational levels thus occupied by the system may be represented by horizontal lines and indicated by appropriate vibrational quantum numbers. If sufficient energy is supplied so that system occupy the vibrational level represented by Vd, the corresponding internuclear distance should become infinity, that is, the molecule should dissociate into atoms. However, this usually does not happen because before this stage is reached, the electron jumps to the higher energy level, that is, electronic transition takes place, and the dissociation will take place only of the molecule in the higher energy level. Now, every electronic state has its own potential energy curve. Two such curves for the lower electronic states are shown in figure by 1 and 2 respectively. They differ in the fact that the minimum of the potential curve for the excited state is at a larger internuclear distance than the ground electronic state. The dissociation energies for the two states are different as shown in figure, that is d2 is less than d1. This is evidently due to the fact that the bonding in the excited state is weaker than in the ground state. The vertical distance between the minima of the two curves gives the difference between the electronic energy of the two states. The transition between the two electronic states take place according to the Frank-Condon principle explained below. According to this principle, nuclei being much more massive than electrons, and electronic transition takes place much more faster than the nuclei can oscillate to change their internuclear distance, and electronic transition take place from an extreme end of a vibrational level, for example from A or A dash, because the velocity of the atoms is zero at these positions and they spend maximum time at these points. As internuclear separation remains the same, the transition can be represented by a vertical line, for example from point A dash to a point C of the upper curve. Note from potential energy minimum of lower curve to that of upper curve, the new vibrational level must be one which is nearest to point C. Counting levels, it appears that the excited molecule will be in the third or fourth vibrational level of state 2. This explains why in the electronic transitions there is no simple selection rule for the transitions among the vibrational levels. All types of transitions from lowest vibrational level to any of the vibrational levels of higher electronic state are possible. It may be mentioned here that according to quantum mechanics, the transition from the lowest level V is equal to 0 take place from the midpoint of the vibrational level and not from the extreme positions. Each vibrational level has a large number of very closely spaced rotational levels which have not been shown in the diagram. Note when the transition takes place from vibrational level of the lower electronic state to some vibrational level of the upper electronic state, it is accompanied by a number of transitions between the rotational levels. The result is a group of closely spaced lines called a band. Since a number of vibrational transitions take place, a group of bands called the band system is obtained. Further, as the transitions take place between many different electronic states, the result is electronic band spectrum consisting of several band systems. If electronic transitions similar to A-C take place, the result is an absorption spectrum consisting of a number of vibrational bands. If, however, a transition similar to BD take place where point D represents the vibrational level corresponding to which the internuclear distance is infinity. The molecule dissociates. Thus, when such a transition takes place, the absorption spectrum consists of a number of bands corresponding to transitions from the ground state to definite vibrational levels in the upper state, but these bands will converge and finally pass into a continuous region or continuum which has no fine structure. The point at which the continuum starts is called the convergence limit. The frequency and hence the energy corresponding to this limit gives the dissociation energy of the molecule. However, it is important to note that after dissociation, atoms are produced in the electronically excited state and not in the ground state. Hence, to obtain the energy of dissociation into ground state atoms, the excitation energy of the atoms must be subtracted. Lastly, it may be pointed out that if the minimum of the upper electronic state is nearly at the same internuclear distances as that of the ground electronic state, the transitions from V is equal to 0 of the ground state to V is equal to 0 of the upper state is the strongest. It goes to that vibrational level of state 2 for which the probability density is maximum. This is calculated from the square of the amplitude of the wave function, as the vibrational energy levels can be represented by waves. Thank you. Electronic spectrum of a diatomic molecule as shown in figure. In case of diatomic molecule, when a photon is absorbed by the molecule, the most probable electronic transition that take place according to Frank Condon principle is from V is equal to 0 of the lower electronic state to V is equal to 2 of the higher electronic state. This is called 0 to 2 transition. Other transitions from V is equal to 0 level of the ground electronic state to different vibrational levels of the excited electronic state also take place, but with much lower probabilities. Thus, the transition 0 to 2 has the maximum intensity, whereas other transitions have some smaller intensities. The result is a spectrum of the type. Now, selection rules for electronic transitions in molecules. In order to understand selection rules for electronic transition in molecules, we should first understand a few terms and symbols to be used there. In parity, parity represents the behavior of an orbital with respect to inversion. It is used for molecular orbitals of homonuclear diatomic molecules. We consider a point in the molecular orbital and note the sign of the orbital. Then we travel equal distance through the center of the molecule to a point that is center of inversion or the other side. This operation is called inversion. If at this point the orbital has the same sign, it is said to have even parity and is denoted by G from Girard, German word for even. If the orbital has opposite sign, then it is said to have odd parity and is denoted by U for ungirate, uneven. The parity designations apply only to homonuclear diatomic molecules because heteronuclear diatomic molecules like HCl do not have center of inversion as shown in figure below. A bonding sigma orbital has even parity and is written as sigma G. A sigma star orbital has odd parity and is written as sigma U. A bonding pi orbital has odd parity and is denoted as pi U, and a pi star orbital has even parity and is denoted by pi G. Multiplicity of state. The ground or excited electronic state of any species may have one or more unpaired electrons with spin in the same direction or opposite direction. If S represents total spin quantum number, then 2s plus 1 gives the spin multiplicity of the state. If S is equal to 0, multiplicity of state is equal to 1. It is called singlet state. If S is equal to half, multiplicity is equal to 2 into half plus 1 is equal to 2. It is a doublet state. If S is equal to 1, multiplicity is equal to 3. It is called triplet state, and so on. For example, in the ground state, H2 positive has only one electron. Its multiplicity is equal to 2. Similarly, O2 molecule in the ground state has two unpaired electrons with parallel spins. Its multiplicity is equal to 3. And number 3 is term symbols of molecules. These symbols give complete information about the state of the molecule. that is orbital angular momentum, multiplicity and parity depending upon the component of the total angular momentum about internuclear axis. They are given the symbols sigma, pi, delta, etc. as follows. Component of the total orbital angular momentum about internuclear axis: 0, plus minus 1, plus minus 2. Symbol as 0 for 0 is sigma, plus minus 1 is for pi, and plus minus 2 is delta into h upon 2 pi. To the above symbols, multiplicity is added on the left as a superscript and parity is added as a script on the right. For example, the single electron in H2 positive in sigma molecular orbital has 0 orbital angular momentum, hence the term symbol is sigma. Further, it has multiplicity is equal to 2, and then parity of the only occupied orbital is Z star. Therefore, full term symbol is 2 sigma g. The term symbol for any closed cell homonuclear diatomic molecule is 1 sigma g because the spin is 0. There is no orbital angular momentum from a closed cell and the overall parity is Z. If there is only one pi electron outside a closed cell, its orbital angular momentum about the internuclear axis is equal to 1 unit. Hence, the term symbol is pi. If there are 2 pi electrons, the term symbol may be sigma or pi. The term symbol sigma will be used if the electrons are orbiting in opposite directions, which can be so if they occupy different orbitals. The term symbol pi will be used if the 2 pi electrons are orbiting in the same direction, which can be so if they occupy the same pi orbital. In case of oxygen, in case of O2, in the ground state, the 2 pi electrons occupy different orbitals with parallel spin and the overall parity of the molecule is equal to closed cell into G is equal to G. Hence, the term symbol is 3 sigma G. Lastly, a superscript plus or minus on a sigma term symbol is added to show the behavior of the molecular wave function on reflection in a plane containing the nuclei. In case of O2, one electron is in 2 pi x, which changes sign on reflection in the YZ plane, and the other is in 2 pi y, which does not. The overall reflection symmetry is therefore closed cell into plus into minus is equal to minus. Hence, the full term symbol is 3 sigma minus of G. Now we give below the selection rules for transitions between different states of the molecule. If there are several electrons, the overall parity is calculated using the method G into Z is equal to G, U into U is equal to G, U into G is equal to U. The rule has been generated by taking G is equal to plus 1 and U is equal to minus 1. Only those transitions are allowed between the states for which the difference in the component of the orbital angular momentum along the z-axis is equal to 0 plus minus 1. The sigma minus sigma, pi minus sigma, and del minus pi transitions are allowed, but del minus sigma is not allowed. The transitions are allowed only between the states having same multiplicity. The singlet and triplet transitions may occur, but singlet triplet transitions are forbidden. Sigma dash minus sigma dash and sigma dash minus sigma negative minus sigma negative transitions are allowed, but sigma positive minus sigma negative are not allowed. Only those transitions are allowed which are accompanied by a change in parity. Thus, G to U and U to G is allowed, but G to Z and U to U transitions are forbidden. This is known as Laporte selection rule. Thank you.